William S. Knudsen found himself in a Pentagon conference room during May 1940, confronting a gathering of skeptical Army generals who evidently perceived his proposals as utterly outlandish. This 61-year-old Danish immigrant, whose remarkable ascent had taken him from the humble position of a bicycle mechanic to the esteemed presidency of General Motors, had just articulated a commitment that bordered on the fantastical. He assured the military brass that he possessed the capability to manufacture tanks with the same efficiency and scale that Detroit employed for constructing Chevrolets. Thousands of these formidable machines would stream off assembly lines at a pace so astonishing that the sheer volume would appear to defy belief. The assembled generals exchanged incredulous glances. One even permitted himself a derisive chuckle. It was a well-known fact that America's entire tank production for 1940 had barely managed to reach a meager 331 units over the course of the full year. Knudsen, however, was boldly asserting the feasibility of producing hundreds of tanks each month from conventional automobile factories, operated by civilian personnel who had, in all likelihood, never even laid eyes upon a military vehicle. Yet, Knudsen was not engaging in mere bluster. He had dedicated 3 decades to meticulously mastering a concept that the military had never contemplated applying to the exigencies of warfare: the groundbreaking Ford production philosophy. Stay with us and watch the end of the video. We will be grateful for your like and subscription. While European nations persisted in their traditional methods of constructing tanks, akin to medieval artisans laboriously forging swords, each unit crafted with painstaking individual attention, Knudsen perceived these complex machines as nothing more than another consumer product, primed and ready for the efficiencies of mass production. The revolutionary Model T had profoundly impressed upon him the fundamental principle that inherent complexity could be drastically diminished when meticulously dissected into a series of simple, highly repeatable steps. A tank, in his pragmatic view, was not some mystical, esoteric weapon. It was a composite of steel, rivets, an engine, and tracks. If American industry could successfully construct 15,000 automobiles daily across the nation, then, by logical extension, it could certainly produce 500 tanks. The arithmetic was undeniably straightforward. The actual implementation, however, promised to be an arduous and hellish endeavor. The Army's Ordnance Department harbored a profound disdain for every facet of this audacious proposition. Their engineers had invested countless decades in perfecting tank designs through a process of small-batch, custom manufacturing. Each M2 medium tank necessitated the expertise of highly skilled machinists, working diligently from intricate blueprints, meticulously hand-fitting components, and treating every single vehicle as a unique, singular creation. Production, consequently, advanced at a glacial pace precisely because such a high degree of craftsmanship inherently demanded considerable time. Knudsen's radical proposal, therefore, was perceived as a direct affront to that entire established philosophy. He aimed to de-skill the manufacturing process, to fragment it into steps so rudimentary they were virtually idiot-proof, to employ any available individual off the street, and to churn out identical machines with relentless efficiency. To the entrenched ordnance officers, this was not a vision of enhanced efficiency. It was nothing short of industrial barbarism. One particularly vocal colonel famously characterized it as the automotive industry's arrogance, thinking war is just another product line. Knudsen, however, had encountered and overcome far more severe criticism in his illustrious career. As far back as 1913, Henry Ford's competitors had leveled precisely the same accusations concerning the efficacy of assembly lines for automobiles, only to be utterly eclipsed by Ford's innovative methods. Now, Knudsen was staking America's very survival on the application of that identical, uncompromising industrial logic to the production of armored vehicles. He had already undertaken the preliminary calculations with meticulous precision. Detroit, he noted, possessed a staggering 4.5 million square feet of factory space lying dormant in the wake of the Great Depression. The necessary machine tools were already in existence. The workforce was tragically unemployed and desperately eager for work. The sole missing components were the requisite official permission and a tank design sufficiently simplified to facilitate true mass production. When Britain's detailed specifications for the new M3 medium tank arrived in July 1940, Knudsen immediately recognized a pivotal opportunity. The Army's initial request was for 1,000 units. He, however, quietly instructed his engineers to prepare for an order of 10,000. President Roosevelt formally granted him the necessary authority on May 28, 1940, establishing the National Defense Advisory Commission and appointing Knudsen as its Director of Industrial Production. He would receive no salary, hold no official military rank, yet wielded virtually unlimited power to retool the entirety of American manufacturing for the impending war effort. Knudsen exited the White House meeting and immediately placed a call to Detroit. Chrysler's ambitious tank arsenal was slated to break ground within a mere 90 days. He then presented them with an audacious target that caused even his own seasoned engineers considerable apprehension: the production of one tank every hour within 2 years. This was not merely an aspirational goal, it was an unyielding demand. The stark reality was that either American industry would achieve this seemingly impossible feat, or the relentless Nazi war machine would prove unstoppable. There existed no middle ground. The critical race had officially commenced, and Knudsen had just committed to winning it using a civilian workforce that, at that precise moment, did not even know what a tank looked like. The devastating attack on Pearl Harbor fundamentally altered the landscape overnight. On December 8, 1941, Knudsen's previously theoretical production plans instantly transformed into America's most vital lifeline. The telephone lines at the War Production Board glowed incandescently as factory managers across the industrial heartlands of Michigan, Ohio, and Pennsylvania received identical, urgent directives. Cease production of whatever you are currently manufacturing and immediately commence building tanks. Suddenly, the Cadillac plant in Detroit, which had for years meticulously stamped out fenders for luxury automobiles, was now expected to forge robust tank turrets. Fisher Body, renowned for crafting sleek, aesthetically pleasing automobile curves, received blueprints for armored hulls, a stark departure from their usual work. This was an unprecedented undertaking. There existed no comprehensive manual titled, "How to Convert Your Buick Factory into an Armory in 3 Weeks." They were, quite literally, inventing the entire process as they went along. While formidable German panzers relentlessly rolled across the vast expanses of North Africa and resilient Soviet T-34s tragically burned in the embattled Ukrainian fields, the chaotic scene at the Chrysler Tank Arsenal in Warren, Michigan, during January 1942, bore less resemblance to precision manufacturing and more to a state of controlled panic. Workers arrived at buildings where the concrete floors were still in the process of curing. The very concept of an assembly line existed solely as chalk marks scrawled upon the bare ground. Crates containing essential tank components arrived ceaselessly, often before anyone had determined appropriate storage locations, resulting in their haphazard piling in parking lots, inadequately protected under tarps. Forklifts navigated precariously between construction crews, who were still in the midst of installing crucial overhead cranes. The initial M3 Lee medium tanks assembled there in April 1942 were, in essence, meticulously hand-built, with each vehicle requiring a laborious 2 weeks to complete, a pace even slower than the artisan craftsman approach Knudsen had so vehemently promised to supersede. Engineers, often covered in grease and sweat, stood directly on the factory floor, literally revising and rewriting blueprints in real time as they discovered that manufacturing tolerances which had functioned perfectly in controlled prototypes utterly failed when scaled up for mass production. Training the vast new workforce emerged as an unanticipated nightmare. While retooling an entire building could be accomplished in a matter of months, the challenge of transforming a recently laid-off restaurant cook into an individual capable of welding armor plate that absolutely had to withstand armor-piercing rounds was monumental. The traditional approach, involving apprenticeships spanning several years, was an utterly impossible luxury given the urgency of the war. Knudsen's astute training director, a former Ford efficiency expert named Carl Bailey, ingeniously devised a radical solution to this pressing problem. They meticulously dissected the complex skill of welding into precisely 17 specific techniques that were absolutely essential for tank production. Nothing more, nothing less. A new recruit was not expected to become a master welder in the traditional sense. Instead, they were rigorously trained to execute one perfect weld in one very specific location, repeating this singular task tirelessly for 10 hours a day. It was, in essence, the assembly line philosophy rigorously applied to human beings. Critics, predictably, decried this method as dehumanizing. Bailey, however, steadfastly maintained that it was the only viable pathway to construct 1,000 tanks a month with a workforce comprised of individuals who, just 3 weeks prior, had never even held a welding torch. The critical material bottlenecks very nearly suffocated production before it could even truly begin. Armor plate represented the most significant constraint. Only a handful of American steel mills possessed the immense rolling capacity required to produce the exceptionally thick, hardened steel necessary for tank hulls, and these mills were already severely backlogged with orders for vital shipyards. In February 1942, Knudsen personally visited Bethlehem Steel's sprawling plant in Pennsylvania and extended an offer that the company's CEO found impossible to decline: substantial government financing for the construction of a brand new plate mill that would triple their output, but only on the strict condition that they delivered the very first run of this specialized steel to Detroit within 90 days. Astonishingly, they achieved this monumental task in just 87 days. Concurrently, the persistent shortage of materials compelled engineers to exercise considerable ingenuity and creativity. The M3's traditional riveted construction, a feature that staunch traditionalists had vehemently insisted upon, rapidly became a significant liability. Rivets consumed valuable time and necessitated precisely pre-drilled holes with exacting tolerances. Welding, while inherently faster, demanded a higher degree of skill from the operatives. The pragmatic compromise involved an accelerated welding training program, a simplification of joint designs, and an acceptance of a 15% reject rate that the stringent quality control measures would effectively catch. By March 1942, the Chrysler production line finally began to achieve a consistent rhythm, producing 4 M3 Lees per day. While still far from realizing Knudsen's ambitious vision, it represented undeniable, crucial forward momentum. Then, the Army once again dramatically shifted its requirements. They now desired the new M4 Sherman tank instead. This was undeniably a superior design, but it came with an entirely distinct set of production requirements. Every single jig, every specialized tool, and every meticulously developed training program that had been built around the M3 became instantly obsolete. Knudsen, however, remained unfazed. He had, in fact, been anticipating such a development. Warfare, he understood, does not patiently await perfect conditions. One must adapt rapidly and decisively, or face inevitable defeat. The comprehensive retooling process commenced immediately, even as M3s were still steadily rolling off the existing production lines. 2 distinct assembly lines, 2 different tank types, operating within a single factory, with absolutely zero margin for error. This was the stark reality of industrial warfare, American style. The M4 Sherman, which arrived on blueprint paper in August 1941, was, from a mass production perspective, a 30-ton mechanical nightmare. It contained approximately 8,000 individual parts, and this count did not even include the staggering 50,000 rivets some variants utilized. The formidable Wright R-975 radial aircraft engine alone comprised 847 distinct components. The complex transmission system required 23 precision gears, each meticulously machined to tolerances as fine as 1/1000th of an inch. The innovative vertical volute suspension system employed 48 bogie wheels per tank, with each wheel necessitating individual rubber cushioning. Army Ordnance had meticulously designed it primarily for battlefield superiority, not for streamlined factory efficiency. Knudsen's engineers, upon reviewing the daunting specifications, immediately recognized that their task was a surgical one. They had to dissect this mechanical beast, simplify every conceivable aspect, and render it so straightforward that even someone's grandmother could competently assemble a section without making a critical error. The pivotal breakthrough in the monumental effort to produce the Sherman tank emerged from the ingenuity of John Willis, a distinguished GM engineer who had dedicated 2 decades to perfecting Cadillac transmissions. In September 1941, he convened his team and presented a revolutionary blueprint on a blackboard. Rather than conceiving the Sherman as an indivisible, monolithic entity, he proposed dissecting it into 7 primary subassemblies: the hull, turret, engine, transmission, suspension, electrical systems, and armament. These distinct components could then be fabricated concurrently in disparate locations before being meticulously unified during the final assembly stage. Each of these critical subassemblies, he posited, would necessitate its own dedicated production line, funneling its output into the overarching manufacturing artery. This innovative modular approach promised to dramatically accelerate the tank's creation by breaking down an overwhelming task into manageable, parallel operations. The sheer scale of this specialized manufacturing philosophy was evident in the hull assembly process alone, which was meticulously subdivided into 22 discrete stations, each assigned a singular, narrowly defined task. For instance, Station 7 was exclusively dedicated to the precise installation of transmission mounting brackets, while Station 14 existed solely for the intricate welding of the bow gunner's hatch. This highly granular division of labor transcended traditional tank construction. It evolved into a meticulously orchestrated industrial ballet, wherein approximately 300 workers each executed their individual movements with impeccable timing and precision, contributing to a seamless flow of production. This systematic deconstruction of the manufacturing process ensured unparalleled efficiency and consistency. For its sprawling River Rouge plant subsequently elevated this manufacturing doctrine to an even more profound level, embracing a philosophy of radical vertical integration. Knudsen, deeply influenced by observing Henry Ford's pioneering vision of factories where raw iron ore entered one end and fully functional automobiles emerged from the other, resolved to apply this comprehensive self-sufficiency to the production of armored vehicles. Consequently, raw steel would arrive at the Rouge plant's formidable blast furnaces, undergo transformation into robust armor plate within their proprietary rolling mill, be precisely cut to size in their stamping facility, and then expertly welded into formidable hulls in Building B. These hulls would then be seamlessly united with engines sourced from Building C, culminating in completed tanks that rolled off the opposite end of the facility a mere 48 hours after the initial steel had been molten. This unparalleled integration dramatically compressed the production cycle and minimized external dependencies. We invite you to stay with us and watch the end of the video. We will be grateful for your like and subscription. Virtually every single component of the Sherman tank, with the notable exception of the main gun, was fabricated entirely on-site at the Rouge plant. This comprehensive in-house production capability offered a profound strategic advantage. Should a design flaw materialize, engineers possessed the immediate capacity to implement corrections directly within the steel mill and observe the rectified component integrated into finished tanks within a remarkably swift 2-day turnaround, thus circumventing the weeks-long delays typically associated with reliance on external suppliers. The pursuit of speed, therefore, was not merely about accelerating individual processes, but rather about systematically dismantling every potential impediment and bottleneck within the entire supply chain. However, the turret component, in particular, presented a unique array of engineering and production challenges that demanded innovative solutions. Indeed, the initial designs for the Sherman turret mandated a colossal casting, a singular, intricately formed piece of steel weighing an imposing 3 tons. At the time, only a handful of foundries across America possessed the specialized capabilities to pour castings of such immense proportions, and even then, the reject rate proved to be brutally high. Nearly 40% of these massive turret castings tragically failed stringent quality inspections, often due to the presence of internal air pockets or the development of critical cracks during the cooling phase. Each such failure represented not only the wasteful remelting of tons of precious steel, but also an agonizing 2-week setback in the production schedule. This intractable problem was ultimately resolved by Pacific Car and Foundry in Seattle, which pioneered an ingenious welded turret design. This innovative approach utilized multiple flat plates meticulously joined together, rather than attempting to create a single, complex casting. While this welded turret was admittedly heavier and perhaps less aesthetically refined, and despite the principled objections from ordnance officers who favored the cast design, its undeniable functionality and, more crucially, its dramatic improvement in production yield to an impressive 94% rendered it an indispensable solution. Knudsen, demonstrating his unwavering pragmatism, promptly sanctioned this design alteration, overriding the objections emanating from Army officials. His singular, uncompromising standard dictated that tanks effectively deployed on the battlefield far outweighed the theoretical perfection of designs confined to a drawing board. This philosophy underscored the urgent imperative of wartime production, where operational effectiveness superseded aesthetic or traditional engineering preferences. The principle of standardization rapidly ascended to the status of religious doctrine, as an increasing number of factories embarked upon Sherman production. A formidable consortium of manufacturers, including Chrysler, Fisher, Ford, Federal Machine, Pacific Car, Press Steel, and Baldwin Locomotive, each initially harbored aspirations of introducing their own design enhancements. Chrysler, for instance, believed its transmission design superior, while Fisher advocated for a distinct engine mount. Knudsen, however, ruthlessly suppressed these individualistic tendencies, unequivocally mandating that every single factory would construct identical Shermans, adhering to identical specifications, utilizing identical tooling, and employing identical manufacturing processes. The absolute interchangeability of parts across every tank, irrespective of its origin factory, became non-negotiable. A transmission fabricated in Detroit, for example, had to seamlessly integrate into a hull produced in Chicago. This stringent requirement transcended mere engineering pride. It was an existential imperative rooted in the harsh realities of battlefield logistics. When a Sherman tank sustained a damaged track in the desolate expanses of North Africa, the repair crews simply lacked the luxury of time to ascertain its factory of origin before selecting replacement components. Standardization ensured that a tank crippled on a Monday could be returned to the fight by Tuesday, whereas variety, in this critical context, equated to death. The burgeoning workforce that streamed through factory gates in early 1942 bore little resemblance to the cadre of precision machinists the Army brass had initially envisioned building their sophisticated tanks. Individuals like Anna Kowalski, who had been serving coffee in a Detroit diner just 2 weeks prior, suddenly found herself expertly welding hull plates on the Chrysler assembly line. James Washington, a 58-year-old sharecropper from Alabama, whose most complex operational experience had been guiding a mule plow, was now meticulously installing transmission assemblies. Margaret Chin, a woman barely 5 feet tall, navigated the confined spaces of turret compartments to meticulously wire electrical systems, accessing areas engineers had mistakenly assumed only smaller men could reach. By mid-1942, an astonishing figure of over 40,000 individuals were engaged in Sherman production across numerous plants, and a staggering 65% of this workforce possessed absolutely no prior manufacturing experience. Knudsen had presciently anticipated this demographic shift. He firmly believed that wars are not won by patiently awaiting the emergence of a skilled workforce. Rather, one must actively cultivate expertise from whomever is available. The training system, ingeniously devised by Bailey, was brutally efficient precisely because it jettisoned the antiquated notion of cultivating well-rounded craftsmen. On her inaugural day, Anna was not burdened with theoretical welding principles, metallurgical intricacies, or the optimal torch angle for a multitude of materials. Instead, her instruction was laser-focused on mastering a single, specific weld, the vertical seam where the hull side met the hull bottom on the M4A3 variant. That was the entirety of her initial curriculum. Her instructor, a seasoned pipeline welder from Texas, dedicated 4 intensive hours to demonstrating the exact torch distance, the precise feed rate, and the specific motion pattern required. She then spent an additional 8 hours diligently practicing on scrap metal, until the weld bead she produced was flawlessly identical on every attempt. By the 3rd day, Anna was seamlessly integrated into the production line, executing that very weld for real, dozens of times per shift. Station 23 became her complete operational universe. Through this hyper-specialization, she attained such proficiency in that singular weld that her reject rate plummeted to below 2%, a performance metric superior to that of many workers possessing a decade of general welding experience. However, the unprecedented velocity of this specialized training inevitably spawned quality control nightmares that very nearly sabotaged the entire production effort. In March 1942, a batch of 47 Sherman tanks failed crucial Army acceptance tests because internal welds on their ammunition racks were found to be substandard. These faulty welds were prone to cracking under the sustained vibrations of firing, posing the catastrophic risk of detonating the tank's own shells and imperiling the crew. Inspectors meticulously traced the root of the problem to a particular training class where the instructor, overwhelmed by the sheer volume of 200 new recruits, had inadvertently cut corners in teaching the critical importance of proper penetration depth. These inadequately trained workers had been producing defective welds for 2 weeks before the issue was finally identified. Consequently, every tank they had touched had to be retrieved from the production stream, painstakingly disassembled, rewelded, and then rigorously reinspected. This colossal undertaking resulted in an 11-day production delay. Knudsen's resolute response, however, was not to decelerate the training regimen. Instead, he mandated the immediate addition of more inspection stations. Henceforth, every 7th Sherman tank was subjected to a complete disassembly by dedicated quality control teams, who meticulously scrutinized every single weld, every bolt, and every tolerance. This process, while undeniably brutal and seemingly wasteful, proved indispensable in intercepting critical problems before any tanks could be deployed to the battlefields. The factories operated relentlessly across 3 shifts, maintaining a 24-hour schedule, 7 days a week. The night shift, spanning from 11 p.m. to 7 a.m., was universally acknowledged as the most arduous. Workers colloquially dubbed it the zombie shift, because the human body simply never fully acclimated to the inverted circadian rhythm, with every biological instinct screaming for rest. Predictably, productivity experienced a discernible drop of 15% during these nocturnal hours, and the incidence of injuries alarmingly doubled. Dorothy Martinez, diligently working on the turret assembly line at Fisher Body, inadvertently succumbed to fatigue and fell asleep while standing at 3 a.m., her hand tragically drifting into a moving conveyor belt. She lost 2 fingers in the accident. Yet, the factory operations did not cease. Her station was seamlessly filled within a mere 20 minutes by a bloater worker, an individual specifically trained for precisely such emergencies. Dorothy, demonstrating remarkable resilience, returned to a different station 3 weeks later, as the loss of fingers did not disqualify one from contributing to the war effort. Only the loss of entire hands did. The stark, cold calculus of wartime production dictated that every individual capable of contributing to the national effort did so. This urgent necessity transformed the factory complexes into peculiar, self-contained communities, as countless workers had relocated from across America, drawn by the promise of defense jobs. They essentially began to live within the orbit of the plants themselves. Chrysler, for example, constructed on-site dormitories capable of housing 3,000 workers. The bustling cafeteria served an astounding 15,000 meals daily across all shifts. A barber shop, a medical clinic, and even a small post office operated autonomously within the sprawling factory complex. Children attended daycare in converted storage buildings, their mothers diligently welding armor plate merely 200 feet away. The hitherto distinct boundary between civilian life and war production utterly dissolved. Workers ate where they toiled, slept in close proximity to their workplaces, and their closest companions were often the individuals sharing their production station. When the public address system announced Allied victories in North Africa during lunch breaks, the resounding cheers reverberated off the steel rafters, fueled by the profound understanding that it was their tanks, forged by their hands, that were securing those triumphs. Each Sherman tank that rolled off the assembly line carried within it a fragment of 40,000 individual narratives, the vast majority of which would forever remain untold. April 12, 1943, represented the monumental juncture at which Knudsen's seemingly impossible promise metamorphosed into tangible reality. At the Grand Blanc Tank Arsenal, an immense complex sprawling across 113 acres of what was once verdant Michigan farmland, Sherman No. 1000 majestically rolled off the production line at precisely 2:47 p.m., a mere 55 minutes after its predecessor, Sherman 999. The plant had, by this point, achieved the rhythmic, ceaseless flow of production that Knudsen had envisioned 3 years prior, a vision that had initially been met with derision by skeptical generals. A single, fully assembled M4A3 Sherman medium tank, every system rigorously tested and certified combat-ready, now emerged from final inspection every 55 to 60 minutes, hour after hour, shift after relentless shift. In stark contrast, the Germans were producing approximately 500 tanks per month across their entire industrial capacity. The Grand Blanc facility alone was matching that formidable number, and it was, crucially, not the sole factory dedicated to the production of the Sherman tank. The Grand Blanc facility, the sole manufacturing site dedicated to the iconic Sherman tank, presented a spectacle of industrial might during its peak operational periods. Traversing the main assembly line felt akin to observing a meticulously orchestrated industrial ballet, albeit one driven by an almost frenetic pace. This colossal production artery extended for nearly half a mile, a testament to the sheer scale of the undertaking. Above, a complex network of overhead conveyors expertly navigated major components, the robust hulls, formidable turrets, and powerful engines, through the vast space, all moving in impeccable synchronicity. Each interval of 6.5 feet along this immense line signified a single minute of relentless production time. At the very genesis of this intricate process, newly welded hulls, still radiating residual warmth from their final joins, arrived from the fabrication building. Workers at Station 1 were allotted a mere 55 seconds to precisely bolt the transmission mounting frame into place before the hull seamlessly advanced to the subsequent station. There was no discernible haste or frantic activity. Rushing invariably led to costly errors. Instead, every single movement was rigorously optimized, down to the specific hand employed to grasp each individual bolt. The personnel, through months of repetition, executing these identical motions approximately 400 times per shift, moved with a mechanical precision that rivaled the very machines they were diligently assembling. Perhaps the most celebrated innovation to emerge from the Grand Blanc production line was its groundbreaking suspended track assembly system. Conventional methods of tank manufacturing necessitated laborers to manually hoist and meticulously position ponderous track sections. This was an exceptionally arduous task, notorious for its physical toll, frequently resulting in debilitating back injuries and significantly impeding the overall production pace. However, the ingenious engineers at Grand Blanc devised a solution. They suspended the heavy tracks from an array of ceiling-mounted cranes, which were perfectly synchronized to move in concert with the main assembly line. As each Sherman chassis steadily progressed along its path, its tracks would descend with impeccable timing, precisely when the suspension bogies were prepared for integration. Workers would then expertly guide these tracks into their designated positions, while pneumatic tools swiftly drove the connecting pins home, completing the entire operation in a mere 90 seconds. What had previously consumed a grueling 45 minutes of intensive manual labor was now accomplished in less than 2. This singular, brilliant innovation, when replicated across 8 dedicated workstations, translated into an astonishing saving of nearly 6 hours per tank. When one considers a daily output of 16 tanks, this efficiency gain suddenly meant the production of an additional armored battalion every week, purely through optimized processes. Stay with us and watch the end of the video. We will be grateful for your like and subscription. The engine marriage station represented a critical juncture where all the disparate elements either coalesced flawlessly or, in a spectacular display, unraveled entirely. Here, the formidable Continental R975 radial engine, a behemoth weighing 1,100 pounds, had to be meticulously mated with the transmission, and then precisely connected to an array of vital conduits, fuel lines, oil lines, coolant lines, the intricate electrical harness, and the exhaust system. All of this complex integration had to be executed within an unforgiving 12-minute window. For skilled workers enveloped each tank, engaging in a precisely choreographed sequence of actions. Worker 1 deftly lowered the massive engine using an overhead hoist, while Worker 2 expertly guided it onto its mounting studs. Simultaneously, Worker 3 connected the transmission coupling, as Worker 4 diligently ran the electrical connections. Remarkably, verbal communication was entirely absent. Their coordination relied solely on a series of precise hand signals. The deafening cacophony, a constant symphony of hammering, welding, engine testing, and the screeching of metal, rendered conversation utterly impossible in any case. They had performed this exact sequence with such unwavering repetition that verbal cues had become superfluous, each worker instinctively knowing the next move of their colleagues through pure, ingrained muscle memory. Quality control, in this high-stakes environment, transcended mere procedure to become an almost sacred doctrine, for speed without inherent reliability was utterly meaningless. Consequently, every single tank produced at Grand Blanc was subjected to the grueling death run, a formidable 3-mile course meticulously laid out within the factory grounds. This course was an engineering marvel in itself, featuring treacherous mud pits, precipitous hills, abrupt, sharp turns, and a multitude of obstacles specifically engineered to push every system of the Sherman to its absolute limit. Engines were mercilessly run at full throttle, transmissions were shifted through every gear under immense load, and suspensions were forced to absorb impacts that precisely simulated the brutal conditions of a battlefield. Should any component falter, be it a telltale oil leak, a grating transmission grind, a thrown track, or an electrical malfunction, the Sherman in question was immediately pulled from the line. The defect was then meticulously traced back to its originating station, and the worker deemed responsible was promptly retrained on the specific procedure to ensure such an error would not recur. The initial reject rate hovered around 8%, which statistically meant that approximately 1 in every 12 tanks failed to pass the rigorous initial testing. However, these 8% of failures were not seen as mere losses. Rather, they represented a crucial filter, ensuring that the remaining 92% of tanks reached the battlefields of North Africa, Italy, and eventually the beaches of Normandy with their systems thoroughly proven under immense stress. No individual wished to have their name associated with a tank that tragically failed in combat due to inadequate training or oversight in production. By the summer of 1943, the cumulative American Sherman production from all contributing plants reached an astonishing 2,020 tanks in July alone. This single month's output dramatically surpassed the total German tank production for the entirety of 1941, underscoring the formidable power of American industry. The assembly line concept had delivered precisely what William S. Knudsen, the visionary behind the wartime production effort, had promised. It had successfully transmuted America's vast industrial capacity into an unstoppable deluge of armored vehicles. Soviet officers, visiting the Detroit factories, were reportedly left speechless as they observed Shermans emerge with metronomic regularity, later conveying to Stalin that American production capability was quite simply beyond their comprehension. The British, who received thousands of Shermans through the vital Lend-Lease program, were able to rebuild entire armored divisions around these American-made tanks because their own domestic production simply could not match the sheer volume. The 60-minute Sherman was not merely a remarkable manufacturing achievement. It marked the pivotal moment when industrial capacity itself became a weapon more strategically decisive than any conventional firearm. A somber telegram, delivered to Knudsen's office on February 18, 1944, carried the kind of news that could metaphorically transform bustling assembly lines into silent graveyards. reports from American tank crews in North Africa detailed catastrophic failures when their Shermans engaged the formidable German Panther and Tiger tanks. Shermans were igniting after sustaining single hits, their comparatively thin armor proving easily penetrable. Crews were tragically incinerated inside what soldiers grimly dubbed Ronsons, a macabre reference to the cigarette lighter advertised for its ability to light on the very first strike. The Sherman's 75mm main gun proved incapable of penetrating German frontal armor beyond a mere 500 yards, compelling Sherman crews to close to suicidal engagement ranges. Morale plummeted, with crews reportedly refusing to board their tanks, and some units even experiencing escalating desertion rates. The Army urgently needed immediate solutions, yet shutting down critical production lines for a complete redesign was simply not an option. The factories were relentlessly producing 1,500 Shermans monthly, and General Eisenhower required every single one for the impending Normandy invasion. The dedicated engineering team at Chrysler was confronted with a seemingly impossible equation. They had to rectify critical vulnerabilities within the Sherman design without halting the continuous flow of the production line. A complete, ground-up redesign was unequivocally off the table. With a mere 4 months remaining until D-Day, tanks already deep in the production pipeline had to reach Europe fully combat-ready. The solution, surprisingly, emerged directly from the harrowing battlefield reports themselves. Crews were ingeniously jury-rigging their own field improvements, welding spare track sections onto the hull fronts for rudimentary additional armor, sandbagging vulnerable ammunition storage areas, and even attaching logs and spare wheels as improvised protection. If soldiers could modify tanks in active combat zones using scraps, then perhaps the factory could systematize those very modifications during the actual production process. Thus, the revolutionary concept of midstream retrofitting was born. The audacious idea of altering the product as it moved down the assembly line without ever disrupting the essential flow. The redesign of the ammunition storage system was prioritized as it addressed the most lethal flaw. Early Sherman models stored their 75mm shells vertically along the hull sides, a convenient arrangement for loaders, but one that proved catastrophic when the tank was hit. Penetrating rounds would frequently strike the ammunition directly, triggering instantaneous detonations that could violently blow turrets 30 feet into the air. In March 1944, engineers implemented a critical redesign, repositioning the shells to lie flat on the hull floor, where they were encased by water jackets. This innovative, wet stowage system was designed to absorb heat and effectively suppress fires, dramatically reducing the risk of catastrophic secondary explosions. Implementing this profound change mid-production necessitated the seamless integration of 3 entirely new stations into the existing assembly line without causing any slowdown to the overall flow. Station 31A was now dedicated to installing the crucial water jacket systems. Station 31B focused on repositioning the ammunition racks themselves. Finally, Station 31C was responsible for rigorously testing the water circulation system. Tanks entering the line on a Monday might still feature the old storage design, but those departing on Friday were equipped with the life-saving wet stowage. There was no discernible production gap. Consequently, battlefield survival rates for Shermans equipped with wet stowage surged dramatically, from a perilous 60% crew survival to a much more reassuring 85%. The problem of armor enhancement proved to be considerably more challenging, primarily because adding meaningful protection inevitably meant increasing the tank's weight. An increase in weight, in turn, would necessitate a complete redesign of the suspensions, engines, and transmissions, a luxury not afforded by the urgent wartime timeline. The pragmatic compromise arrived in the form of applique armor, bolt-on plates that crews could add in the field based on specific mission requirements. Fisher Body created standardized kits comprising frontal hull plates, adding a crucial inch of armor, along with turret cheek plates and even track guards. These kits were manufactured separately and then shipped alongside the tanks, empowering field commanders with the flexibility to configure their Shermans for specific roles. Tanks destined for leading assaults would receive maximum available armor, while exploitation units would keep weight down to prioritize speed. It was not an elegant solution in design terms, but crucially, it worked. More importantly, it worked without requiring a fundamental redesign of the base Sherman, ensuring that the 6,000 tanks already in the production pipeline did not become obsolete overnight. The upgrade to the 76mm gun presented the single biggest production headache of all. This new, high-velocity weapon possessed the capability to effectively engage and damage German heavy tanks, but its integration demanded a completely different turret, one that was notably larger, heavier, and incorporated significantly modified recoil systems. Ordnance, the military department responsible for weapons, urgently advocated for all new production to immediately shift to the 76mm variant. Knudsen's team, however, pushed back forcefully. Retooling turret production across multiple factories would incur a prohibitive cost of 6 weeks' worth of output, translating to roughly 2,000 tanks that would not reach Europe in time for the critical Normandy invasion. The compromise ultimately reached was a brutal yet practical split production strategy. The Chrysler line would maintain its production of 75mm Shermans at full speed, while the Fisher line would deliberately slow its pace by 30% to retool for the 76mm variants. While this meant a temporary dip in combined output, the essential flow of tanks would not cease completely. By June 1944, both versions were being produced simultaneously, providing battlefield commanders with crucial tactical options rather than forcing a single, inflexible solution for all combat situations. The entire adaptation process, under immense pressure, ultimately unveiled a profound truth that Knudsen had implicitly understood from the very beginning. Assembly lines were not merely rigid mechanical systems. Rather, they were dynamic, living processes capable of evolving and adapting under duress. A more traditional military procurement approach would undoubtedly have halted all production, demanded an elusive perfection, and ultimately delivered the ultimate tank 2 years too late. The assembly line philosophy, in stark contrast, championed a different mantra. Keep building, fix problems incrementally, and trust that sheer volume creates opportunities that perfection never could. A Sherman equipped with wet stowage and applique armor might not have been inherently superior to a Panther in a one-on-one engagement. However, the strategic reality was that 5 Shermans arriving this month far outweighed the prospect of one perfect tank arriving never. The line kept rolling relentlessly. The modifications continued to be integrated. And, most importantly, the tanks steadfastly kept reaching the soldiers who desperately needed them. That, in the crucible of wartime, was the only metric that truly mattered. Not the pursuit of unattainable perfection, but the undeniable, life-saving presence of vital equipment on the front lines. The stark reality of wartime manufacturing presented a narrative German tank designers would have preferred to avoid. From the early months of 1942 through the summer of 1945, American industrial complexes churned out an astonishing 49,234 Sherman tanks. This figure, when contemplated, vividly illustrates the colossal industrial disparity that ultimately determined the course of armored engagements during the Second World War. In contrast, Germany managed to construct approximately 6,000 Panthers, widely regarded as their premier medium tank, which technically surpassed the Sherman in nearly every specification. Furthermore, they produced roughly 1,350 Tigers, formidable behemoths capable of neutralizing Shermans from distances where any retaliatory fire proved utterly futile. While German engineering might have claimed theoretical victory on paper, the practical battlefield saw this advanced design inundated by a relentless surge of American production. For every Panther that met its demise, 3 additional Shermans invariably appeared, underscoring a fundamental truth: mathematical superiority, when quantity reaches biblical proportions, cares little for individual quality. The broader context provided by Soviet production figures further amplifies this critical insight. The T-34, a contender for the war's most effective tank design, saw an estimated 84,000 units roll off assembly lines. When combined, the armored vehicle output of the United States and the Soviet Union collectively soared to approximately 180,000 units. Conversely, the combined efforts of the Axis powers, Germany, Italy, and Japan, resulted in a mere 50,000 vehicles. This meant the Axis found themselves embroiled in a grueling 3-front conflict against adversaries, whose tank production rate was nearly 4 times their own aggregate output. German tank crews frequently recounted the harrowing psychological experience of decimating 5, 6, or even 7 Shermans in a single skirmish, feeling a fleeting sense of triumph, only to witness a fresh wave of 10 more cresting the distant horizon. Such tactical prowess became strategically meaningless when the enemy possessed the capacity to absorb losses that their own war economy simply could not sustain. Each Sherman tank that was brewed up represented perhaps 2 hours of American production time, whereas every Panther loss signified 2 weeks of German resources, a deficit they were utterly incapable of recouping. This profound advantage in replacement rates utterly dismantled the established German armor doctrine. Panzer divisions in 1944 had been conceived around the principle that qualitatively superior tanks, skillfully operated by seasoned crews, could overcome numerically larger forces through sheer tactical brilliance. This strategy had indeed proven successful during the invasions of Poland and France, and in the initial phases of the Russian campaign, when German tanks were technologically advanced, crews were exceptionally well trained, and logistics could effectively sustain units. However, by late 1944, these foundational assumptions had crumbled. A Panzer division suffering the loss of 30 tanks in battle might face a 3-month waiting period for replacements, a direct consequence of German factories being unable to maintain pace. In stark contrast, an American armored division losing 50 Shermans would receive full replacements within a mere 2 weeks, sometimes even days. Units that should have been rendered combat ineffective after heavy engagements were restored to full strength before German intelligence could even update their casualty assessments. The American forces were not triumphing through sophisticated tactical maneuvers. They were prevailing through the inexorable force of industrial inevitability. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. The devastating impact of the strategic bombing campaign on German production only exacerbated this already catastrophic gap. The Alket factory in Berlin, a crucial producer of Stu-G3 assault guns, sustained a direct hit from B-17 bombers in March 1944 and required a full 4 months to return to its pre-strike production capacity. Similarly, the Henschel plant in Kassel, responsible for constructing the formidable Tiger tanks, endured 6 separate bombing raids between September 1943 and March 1944, each incident resulting in weeks of debilitating delays. Meanwhile, American Sherman production remained entirely untouched by strategic bombing, operating around the clock with 3 shifts daily and benefiting from unfettered access to an abundance of raw materials. Steel shortages never impeded Detroit's manufacturing prowess. Aluminum was plentiful, and rubber was procured from both natural and synthetic sources. After 1943, the ever-widening disparity in resources meant that German factories were engaged in a desperate struggle merely to maintain their existing output, while American factories were relentlessly optimizing their processes to accelerate the construction of even more vehicles. The immense logistical infrastructure generated by Sherman production was nearly as vital as the tanks themselves. Each individual Sherman required a constant supply of spare parts, ammunition, fuel, and specialized maintenance equipment. American factories, therefore, did not merely produce 49,234 tanks, they simultaneously created the entire support apparatus necessary for these vehicles, countless spare transmission assemblies, replacement track sections, comprehensive engine rebuilding kits, and a myriad of electrical components. The legendary Red Ball Express supply routes established in France after D-Day transported an astonishing 12,000 tons of daily provisions, a substantial portion of which was directly attributable to Sherman-related logistics. In stark contrast, German units frequently found themselves compelled to abandon even reparable Panthers due to a critical scarcity of spare parts or the absence of appropriate recovery vehicles. American maintenance battalions, leveraging the principle of standardized, interchangeable parts from any factory, could rebuild a severely damaged Sherman and return it to active duty within a mere 72 hours. The assembly line's foundational emphasis on interchangeable components meant that the entire logistical system operated with a comparable level of efficiency, mirroring the speed of production. The tank crews themselves became an integral component of this overwhelming quantitative advantage. By 1944, the training of a German panzer crew could take 6 months. Primarily due to a critical lack of fuel for extensive practice maneuvers. Experienced instructors were perishing on the front lines at a rate faster than they could be replaced, and every tank allocated for training represented one less vehicle available for combat. American tank training, however, benefited from an abundance of resources, including Sherman mock-ups, unlimited ammunition for practice, dedicated training facilities safely removed from the combat zones, and, crucially, ample time. A crew could undergo 4 months of comprehensive training stateside before being deployed to Europe, where they would receive a brand new Sherman that had rolled off the assembly line the very week of their embarkation. The industrial system, therefore, was not merely producing tanks. It was simultaneously generating a steady stream of trained crews to match these prodigious production rates. By 1945, the American armored force had evolved into a perfectly integrated, self-sustaining system, where production, training, logistics, and replacement mechanisms all moved with the same unrelenting pace. Germany, facing such systematic dominance, simply never stood a chance. The Shermans did not necessarily need to be individually superior. Their decisive impact stemmed from their sheer, ceaseless presence on the battlefield. William S. Knudsen passed away on April 27, 1948, in Detroit, largely in obscurity. There was no state funeral, no grand memorial on the National Mall. The New York Times afforded him a mere 4 paragraphs on page 23 of its edition. Most Americans, whether they had driven Chevrolets or served bravely in Sherman tanks, remained entirely unaware of his identity. Yet, this was the individual who had received a truly unique honor in American history. President Roosevelt had directly commissioned him from civilian life to the rank of lieutenant general in January 1942, making him the only person ever to bypass every single rank from private to a 3-star general. He wore the uniform for 3 years, never once commanded troops, never fired a shot in anger, and yet arguably contributed more to securing victory in World War II than most battlefield commanders. General Dwight D. Eisenhower himself later asserted that Knudsen's contribution was as critical as that of any general. Despite this, history often relegated him to footnotes, while celebrating the tank commanders who operated the very vehicles his ingenious system had brought into existence. The assembly line doctrine, perfected by Knudsen, did not perish with him. Instead, it metastasized into every facet of military production. The manufacturing of the B-24 Liberator bomber at the Willow Run facility directly applied Sherman assembly principles, eventually achieving an astonishing output of 1 bomber every single hour. The Liberty Ship program, building vital cargo vessels, utilized modular construction methods directly copied from tank production, allowing each ship to be completed in a mere 42 days. In the post-war era, the Pentagon permanently embedded civilian production experts into its military procurement processes. The concept of America as the arsenal of democracy was no longer merely poetic language. It became official, institutionalized doctrine. The nation would never again depend on slow, bespoke military contractors hand-building weapons. Henceforth, everything from colossal aircraft carriers to individual artillery shells would be designed with mass production as a primary consideration from its inception. The new understanding was clear. Future wars would be decisively won in factories before soldiers ever fired the first shot. The Cold War defense industry ultimately became Knudsen's most profound legacy. When the Soviet Union emerged as the new formidable threat, American military planning unequivocally centered on maintaining a decisive production advantage. Weapon systems such as the M48 Patton tank, the M113 armored personnel carrier, and the M16 rifle were all conceived with manufacturability as a paramount requirement, not a secondary consideration. Defense contractors were compelled to demonstrate their capability to produce weapons at an immense scale, rather than merely constructing superior prototypes. This overarching philosophy reached its zenith with the M1 Abrams tank in the 1980s. The Lima Army Tank Plant in Ohio, a facility purpose-built on the very principles of Sherman production, could produce 120 Abrams tanks monthly, meaning a 60-ton main battle tank rolled off the line every 6 hours. While these numbers did not quite reach the unprecedented scale of Sherman production, the underlying philosophy remained absolutely identical: to overwhelm potential adversaries through sheer production capacity, rather than relying on marginal technical superiority. The civilian production model's influence extended far beyond military hardware. It fundamentally transformed how America conceptualized industrial mobilization. The 1950 Defense Production Act, which remains an active statute today, granted the president sweeping authority to compel private companies to prioritize government contracts during national emergencies, precisely what Knudsen had informally orchestrated in 1940-41. The establishment of the Strategic National Stockpile, FEMA's Comprehensive Emergency Response Planning, and even the rapid production of COVID-19 vaccines in 2020-21 all drew upon frameworks originally developed during the critical Sherman production crisis. The revolutionary ideas that civilian industry could be swiftly converted for emergency production, that private companies and government entities could forge massive partnerships, and that speed held precedence over perfection in times of crisis, these were not innate assumptions. Knudsen, however, conclusively proved their viability at a time when most experts had deemed them impossible. Yet, This pervasive doctrine carried inherent costs that few were willing to openly discuss. The assembly line philosophy, in its zealous prioritization of quantity, sometimes fatally compromised quality. Sherman crews tragically paid this price in theaters like North Africa and Normandy, often perishing inside tanks that were merely good enough to produce rapidly, but offered insufficient protection. The institutional bias toward mass production occasionally led the American military to field equipment that, while readily available, was functionally inferior simply because it could be manufactured faster. The M14 rifle, the M551 Sheridan tank, and the Bradley fighting vehicle all emerged from a system that, at times, valued production speed above genuine combat effectiveness. Knudsen's genius lay in his acute recognition of when quantity unequivocally mattered more than quality, but the powerful system he engineered sometimes applied that very logic even in situations where superior quality should have been the decisive factor. The ultimate historical analysis demands a stark and often uncomfortable candor. It is an undeniable historical truth that the strategic triumph of Knudsen's innovative assembly line methodology decisively secured victory in the Second World War. There exists no serious contention regarding this fact. An astonishing fleet of 49,340 Sherman tanks, fabricated by an industrial workforce largely unacquainted with such complex military machinery prior to the conflict, and deployed through a logistical framework that defied established military conventions and expectations, effectively overwhelmed and dismantled the formidable armored divisions of the Axis powers, not through individual tank superiority, but through an unrelenting, numerical onslaught. Yet, those very same Sherman vehicles were undeniably less capable, quantitatively outmatched, when compared to their formidable German adversaries in terms of protective plating, offensive capability, and the safety provisions for their operating personnel. A tragic consequence was the elevated casualty rate among American armored crews, a direct result of a prevailing manufacturing strategy that consciously favored the rapid deployment of sufficient, functional tanks to the front lines, rather than dedicating resources to the protracted development of theoretically superior, albeit delayed, models. This strategic imperative inevitably prompts a profound ethical inquiry. Was this the correct course of action? From a purely consequentialist historical perspective, the affirmative answer appears evident, given the ultimate triumph of the Allied forces. Nevertheless, for the countless individuals who perished within the fiery confines of those Sherman tanks, the discourse surrounding this decision undoubtedly warrants a far more nuanced and empathetic examination. Fundamentally, Knudsen engineered the industrial apparatus that secured the Allied victory. However, the profound query of whether that apparatus represented the optimal choice remains an unresolved philosophical and moral quandary, one that continues to evoke a sense of unease. Stay with us and watch the end of the video. We will be grateful for your like and subscription. It stands as an indisputable fact that no other non-military individual throughout the annals of American history exercised such a profound and decisive impact upon a monumental military triumph, all while largely receding into obscurity. This remarkable Danish immigrant, whose audacious pledges initially seemed unattainable, unequivocally fulfilled those extraordinary commitments. Subsequently, he quietly faded into the periphery of historical records, a mere annotation, even as the global civilization he had so instrumental in preserving largely consigned his name to oblivion. Such an arc, marked by immense, self-effacing contribution and subsequent public oversight, could arguably be characterized as the quintessential American narrative of the entire global conflict.